Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is the resistor. Our objective today is to take a close look at a common electrical component known as a resistor. We'll discuss fixed resistors and introduce two important electrical relationships known as series and parallel, and how these arrangements dictate total resistance seen by a voltage source. Along the way, we'll discuss a complete path known as a circuit and discuss the influence of shorts and opens inside circuits. I will ambush you with some heavy stuff during the course of this lecture, so be ready. The resistor is a component that resists, controls, or otherwise opposes the movement of electrical charges. This movement of electrical charges is known as current, where current is the effect established through a path by a voltage differential between 2 points. Without resistance, current would be an uncontrolled, potentially dangerous movement of charges. Without voltage, there would be no movement of charges. The oppositional strength of a resistor is a measurable quantity of resistance in units of ohms. If there's more ohms, there's more resistance, and would yield a smaller current for a given voltage. It would be just as easy to say if there are less ohms, there'd be less resistance, and there'd be more current yielded for a given voltage. This important cause-effect and opposition relationship is known as Ohm's law, a very important topic we'll spend another entire lecture on in the near future. Resistors come in several different varieties and shapes, but the ones you'll most likely gain early exposure to are mass-manufactured, two-terminal devices that come in certain standard values and sizes. Just like going to a hardware store to pick up a bolt, you can't expect custom-made sizes and specifications. However, there is a reasonable variety of sizes commonly available that gets the job done at a minimum cost. Operating under the presumption that you are armed with the knowledge of the resistance lecture available at the Big Bad Tech channel, you are no doubt aware that the measurable resistance of a device is a function of three properties, namely the length, cross-sectional area, and material composition, specifically the innate resistivity of the conductive path. If I were to present you with two resistors of absolutely identical physical dimensions, i.e. two resistors of exactly the same length and cross-sectional area, but of notably different resistance values. Let's say this one is 100 ohms and that one 2000 ohms or 2 kilo ohms. What would you presume is the primary difference between them? If you said resistivity, you're right, because the length and the area are the same. At least you're right for our current level of understanding. But this isn't really far from the truth. Be aware that there are some idiosyncrasies between different resistor manufacturing techniques. But we're going to pretend simply by altering the resistivity of the stuff inside our resistor is how we change a resistor's resistance value. Just like a good lab partner, it's what's inside that counts. Most likely, you'll deal with carbon film resistors, and sometimes metal oxide film or wire wound resistors for higher power applications. Carbon film resistors are your typical brownish tan dumbbell looking resistor, and these are the ones you'll most likely use in a basic electronics lab. Pretty much the same thing can be said about the external view of a metal oxide film resistor, except they're not beige, but rather the shade of powder blue I'd normally find nauseating, but since it's associated with higher power ratings, I've grown somewhat tolerant of it. Printed on the outside of the insulating case of most resistors is a mysterious color band code we'll spend another lecture at the Big Bad Tech channel learning to decipher. For now, we'll just assume we know the values and worry about the color code later. I really like wire wound resistors simply because they look cool. They got a ceramic tube in the center around which a length of high resistance wire is wrapped. Sometimes these things are pretty big and designed to dissipate a large amount of heat. Carbon composition resistors are kind of like carbon film resistors, except they're typically a darker shade of brown. You may not run across these guys because they're kind of an older technology. On the other extreme end of the size scale, surface mount resistors are super small, almost to the point of too small for humans to handle. We leave that to our robot slaves. Surface mount resistors are used on printed circuit boards for low power applications. These guys don't have terminals but rather conductive ends that slip into sockets on a printed circuit board. Regarding the different physical sizes of resistors, answer this question after some thought. Which has a greater resistance? A super large 100 ohm wire wound resistor? A large 100 ohm metal oxide film resistor? A medium 100 ohm carbon film resistor? A small 100 ohm carbon film resistor? Or a super tiny 100 ohm surface mount resistor? The answer is they all have the same resistance because they're all 100 ohm resistors. Get it? What's the reason for the range of sizes? Isn't it obvious? I'm not going to use a surface mount resistor to carry a lot of current. I'm going to use a big old wire wound resistor with a ceramic tube to dissipate heat. In short, physical size of a resistor has nothing to do with resistance and everything to do with power handling capability. Physically larger resistors have higher power ratings. Most resistors, with the obvious exception of the surface mount, have a conductive lead coming out of each end, or at least two terminals where you can attach other wires. These terminals are used to connect the resistor temporarily inside a prototyping board, or permanently, or at least semi-permanently, by soldering it through mounting holes on a printed circuit board. A prototyping board is a kind of temporary workspace you'll often use in a lab environment. We'll discuss prototyping boards in further detail in later lectures. Either way, the schematic symbol for a resistor is exactly the same regardless of composition. It kind of looks like a tope or a speed bump, and it's there to remind voltage sources that its purpose in an electrical circuit is to slow electrons down or control current in a circuit. The purpose of schematics and symbols like these is to speed up and simplify the representation of electrical circuits. Imagine how long it'd take to draw a circuit using eye-pleasing shades and graphically accurate representations of every single component and wire. Speaking of circuits, realize a circuit is exactly what the term is meant to imply. This is a super important topic, and I'm including it in the resistor discussion because they go hand in hand quite well. A circuit is a complete path or closed loop. The loop could be a single circular, rectangular, triangular, or any other shape forming a complete loop. Or a circuit could be composed of many different pathways, that at least one of which comes back to our starting point. Without at least a single closed loop, there is no circuit, and there is no way conventional current can flow from the positive terminal of a voltage source to the negative terminal. A closed circuit requires a closed path for current to flow. If one has to represent several resistors inside a single circuit, they're often given subscript notations, such as R1, R2, etc. If there's a resistance value and power rating associated with a specific resistor, it can be printed right next to it if it's a small circuit, or perhaps appear on an associated components or parts list if it's a large circuit. If resistors or wires are connected, schematics indicate they're connected by placing a dot at the point of connection. If wires merely pass over or under other wires but do not connect, there will be no dot. Oftentimes you'll see an overpass symbol to indicate passage but no connection. Use this symbol. You'll immediately appreciate the clarity. Regarding the points of connection, these can also be numbered, lettered, or otherwise identified. The common term for these points of connection is the word node. You'll immediately recognize a conflict between component subscript notation and nodal notation using the same numerical identifiers. My advice is to deal with it. Consider this hypothetical scenario. Find V1. Does this mean find the voltage across resistor 1? Or does this mean find the voltage at node 1 with reference to some previously agreed upon reference point, like ground? I don't know. Seek clarification. Consider another scenario in which clarity is desired. Perhaps you're in charge and you're the one responsible for building, testing, and troubleshooting a circuit. You could use a confusing mishmash of unrecognizable symbols. No symbols are planned at all. Or you could perhaps use letters to identify nodes and numbers to identify components, or vice versa. You could have a plan. This isn't a universally followed practice though, and you've got to, as they say, deal with it. If you're building a circuit, you have control. Make it easy on yourself and your lab partner and establish clarity up front. Imagine how well lab will go if you know what you're doing and you're organized. Sticking with nodes for a little, realize a node is a point of common connection. Node A has two components hooked to it, notably the positive terminal of voltage source E and one terminal of resistor 1. Node B has three components hooked to it, one terminal of resistor 1, one terminal of resistor 2, and one terminal of resistor 3. Stepping outside this circuit, this node X has four components hooked to it. This node also has four components connected to it. Yes, it looks a little bit different than our other node with four connections, but deal with it. If you think about it, despite there being different wires and maybe different lengths or different colors of wires, you could just as easily connect all four devices to a single point. This is another tremendous advantage of schematics. They're often known as elemental diagrams, meaning their purpose and arrangement has been simplified and compressed into its elemental or most readable and understandable format. Schematics aren't pictorial, dimensionally accurate drawings of a real physical layout. Resistor 3 and 4, despite being right next to resistor 1 and 2 on our schematic, could for all practical purposes be halfway across the country in Chicago, probably getting stabbed in the back with a broken wine bottle, and only connected to node B via a long, low resistance wire. Regarding wires in our circuits, depending upon your level of accuracy and time commitment, most of the time the resistance of the wires composing our circuit is ignored, given the resistance value are typically much, much smaller than the components you'll be using. Regarding nodes and circuit depictions using schematics, if you're one of those folks from the 1800s that still wears a wristwatch and carries around one of those 10-pound, $300, 1,200-page textbooks, be aware that a large number of those terribly confusing example problems at the end of the chapter really are just purposely poorly drawn schematics. Seek clarity. You do not have permission to change the circuit, but you do have the freedom to change how the circuit is represented. Redraw the circuit in terms you can understand and engage it in the manner you see fit. You can't break the wires, but you can move them around. Think of them as stretchable and bendable conduits. You can't add or remove components hooked to a node, but you can always expand or contract a node, keeping those same components attached to simplify a diagram. In short, think about it, visualize it, draw a picture, draw several pictures. Imagine if you were a conventional current electron being asked to travel through your circuit. Every time you enter a node, ask yourself if you have a choice of exits, and if so, how many. This is the purpose of circuit analysis. Simplify a circuit to its most elemental structure. Returning back to our topic of resistors, realize a 100 ohm resistor dangling off the positive terminal of a DC voltage source is not a circuit, nor is a 100 ohm resistor dangling off the negative terminal of a voltage source. Nor is a 100 ohm resistor with both leads touching the positive terminal, nor is a 100 ohm resistor with both leads touching the negative terminal. Nor is a 100 ohm resistor sitting in the same room as a voltage source a circuit. In short, there are a lot of wrong ways to build a circuit, and often only a handful of right ways to do so. A complete circuit is only established when one lead of a resistor is touching the positive terminal of a voltage source and the other lead is touching the negative terminal of the same source. Once these two connections are made, then and only then can conventional current now flow from our source through our resistor. The polarity or orientation of a resistor does not matter, meaning you can flip it or the voltage source around and connect it however you want, such that current goes either direction. This is not always the case for all components. You'll find other components such as diodes purposely block current in one direction and allow it to flow in the other direction. Other components such as certain types of capacitors can be irreparably damaged if you hook them up incorrectly. Point is, pay attention to the markings on the outside of the component, obey manufacturer's recommendations, and hook it up like you're supposed to. Consider our first complete circuit consisting of a 100 ohm resistor hooked up positive to negative to a voltage source. With a complete circuit, conventional current can now flow from the positive terminal of our voltage source to the negative terminal of the voltage source through the resistor. The question is, how much resistance does the voltage source see? If you said anything different than 100 ohms, please take the time to pause the lecture and viciously slap your hand with a wooden ruler. It's immediately evident that with a single resistor in a single path, the path's complete resistance is that single resistor. Now let's talk about circuits with more than one resistor. If I was to add another 100 ohm resistor to this circuit, I could add it in one of two places. First, I could add it in series, or directly in line with our first resistor. Or two, I could add it in parallel, or to the side of our first resistor. Notice in the case of a series arrangement, I've added another node, or another point of interconnection. However, there still exists only a single path. In the case of the parallel arrangement, I have not added any additional nodes or points of interconnection. I've just added another component to two previously existing nodes. In this case, however, as conventional current enters node A, there is now a choice of paths. This important distinction bears repetition. A series arrangement means there is one path and one path only. A parallel arrangement means there is a choice of paths. This is the fundamental difference between series and parallel configurations, and as we'll learn in later more in-depth lectures on these topics, this simple distinction dictates important circuit-level properties about series and parallel relationships. For now, I'd like us to just focus on the resistance values obtained using different series and parallel arrangements of resistors. Turning our attention to the series relationship, in my opinion the easiest and most self-evident of our relationships, what is the total resistance seen by a voltage source when it must push current through a 100 ohm resistor and then another 100 ohm resistor? It's obvious that the voltage source is now being opposed by 200 ohms of resistance. In a series relationship, resistances add up. It's really that simple. It's like you being in an electronics lab all day and then working in a coal mine all night and then watching these stupid online lectures on your celly on the way to school. By the time you show up to lab the next day, you're going to be dragging because you've been assigned task after task in an unavoidable, inescapable sequence because there is one path. If you want to draw connections to our earlier lecture on resistance, one could visualize series relationships as keeping the cross-sectional area and material composition of our conductive path the same, however simply increasing the length of a path. In the case of two back-to-back 100 ohm resistors, it can be easily simplified as a single resistance with twice the length, in this case 200 ohms. What if we add a third resistor to this series relationship? Let's say we added a 300 ohm resistor in series with two 100 ohm resistors. What's the total resistance now? Obviously the answer is 300 plus 100 plus 100 equals 500 ohms of total resistance. I do not think we need to spend any more time on this topic. It's that simple. Resistance and series relationships add up. However, pause to consider alternate configurations of series relationships. Is this a 300 ohm resistor in series with a 100 ohm resistor in series with a 100 ohm resistor? Yes, it is. Granted, it looks weird, but it's still a single path. Follow the current. This is where you are extremely grateful for the overpass symbol. By pretending you're Johnny conventional current electron leaving the positive terminal of our voltage source, at any time are you presented with a choice of paths? No, at all times you are confined to a single pathway through which all current must flow. This being said, will the current flowing through the 300 ohm resistor be any different from that flowing through either 100 ohm resistor? No, they should be the same because there is only one path. This is the single most important distinction about series relationships that will bear constant, annoying, torturous repetition throughout your time in the basic electronics series. Current in a series relationship is the same because there is but one path. What about this configuration? Is this a 300 ohm resistor in series with a 100 ohm resistor in series with a 100 ohm resistor? Kind of. It's actually a 100 in series with a 300 in series with a 100. What about this one? Is this a 300 in series with a 100 in series with a 100? Again, not really. This is really a 100 ohm resistor in series with a 100 ohm resistor in series with a 300 ohm resistor. Order aside though, what is the final total resistance seen by the voltage source for any of these three configurations? Is it in any way influenced by in which order the individual resistors are encountered? No. Every single configuration, the total resistance seen by the source is 500 ohms. The phrase seen by is a little misleading. When I say seen by, realize what I mean is that the voltage source will behave the same, i.e. produce the same amount of current through any relationship totaling 500 ohms of resistance. In fact, the voltage source would behave the same even if the whole thing was swapped out and just replaced with a single 500 ohm resistor. Is a circuit with a single 500 ohm resistor and two nodes easier to build and troubleshoot than one composed of three different resistors and 4 points of interconnection? I would certainly think so. This is circuit analysis, simplification, gain clarity by reducing circuits to their most elemental form. You do not have to take it all the way home, but you do have to bring it down to its most understandable level. What about this configuration of a 300 ohm resistor and two 100 ohm resistors? Are they in series? Not really. Yes, the resistors are in line with each other, one after another, but there is this huge gaping hole in our circuit right here in the form of an open switch. If you'll recall from our previous lecture on resistance, the resistance of an open switch is infinite. What is the total resistance of infinity plus 300 plus 100 plus 100? The answer is infinity plus 500. There is no way Johnny Electron is going to travel through this circuit because there is so much resistance for this path. That's the point of an open switch. It disables current flow for the series path it's in. Only by closing this switch can our circuit be completed and thereby allow current to flow through it. Again, you'll recall from our previous lecture on resistance, the resistance of a closed switch is 0 ohms. What's the total resistance of 0 ohms plus 300 ohms plus 100 ohms plus 100 ohms? The answer is 500 ohms. An ideal closed switch simply enables our series circuit without influencing it in any other way. An ideal open switch simply disables our series circuit. Can you dig it? This is a very powerful property. Closed switches allow current to flow. Open switches do not allow current to flow. Switches enable or disable entire paths simply by changing their resistance from one extreme to the next. Finally, consider this configuration of a 300 ohm resistor and two 100 ohm resistors. Are they in series? No, not really. In this case, the 300 and one of the 100 ohms are in series. However, this 100 ohm resistor is just dangling off in space. Is there any reason for electrons to move or current to flow in this dead-end path if their intended destination is the negative terminal of our voltage source? No. Conventional current requires a complete path from the positive terminal of a voltage source to the negative terminal of a voltage source. In this case, the voltage source is really only experiencing 300 plus 100 ohms of resistance, or 400 ohms of total resistance. This extraneous resistor dangling off into space is contributing nothing to the total resistance or current controlling opposition to our voltage source. Let's take a break from series or inline relationships and talk about parallel or side-by-side relationships. This arrangement is not nearly as easy to understand and requires some visualization skills. However, I've got a trick up my sleeve in the form of our previous discussion on the three properties that determine the resistance of a conductor, namely length, resistivity, and cross-sectional area. Notice the emphasis. If you've got a single resistor connected from node A to node B, and if you add an identical resistor in parallel to this first resistor connected to the same nodes, think about what Johnny conventional current electron sees when he emerges from the positive terminal of a voltage source and enters node A. He sees not one, but two open and accessible doors. Is it easier for him and the rowdy crowd of electrons behind him to travel to his intended destination when there are twice as many entry points? Think about what I'm asking. Is the voltage source experiencing less resistance when there's more cross-sectional area? The answer is yes. Anytime you add anything in parallel, in effect you're adding more cross-sectional area or more alternate paths for current to flow. Parallel relationships always reduce the total resistance seen by the source to something less than the smallest resistor in the parallel relationship. This is true every single time and is a great way to check your work. I know I have not presented you with any formulas or numbers yet, but if you ever find the total resistance of a parallel relationship larger than any resistor in the parallel relationship, you're doing it wrong, and you need to perform a tactical retreat and reassess your data. Again, formulas and computations aside, what's the resistance of two 100 ohm resistors in parallel? The answer is it must be less than 100 ohms, because there's twice as much cross-sectional area. If there's twice as much cross-sectional area, it stands to conjecture that a 100 ohm resistor in parallel with a 100 ohm resistor is half of 100 ohms, or 50 ohms. Makes sense. What if I put three 100 ohm resistors in parallel? Again, 3 times the cross-sectional area means my source sees 1/3 of 100, or 33.3333333333333333 ohms of resistance. What if I put 100 100 ohm resistors in parallel? You guessed it. With 100 times the cross-sectional area, you see 1/100th the total resistance, because there's 100 100 ohm doors for Johnny Electron and all his rowdy buddies to crowd through. In this case, the source would see only 1 ohm of resistance, and chances are it's cranking out a lot of current because the total resistance is so low. Keeping with this 100 ohm resistor example for just a little bit more. No, I'm not going to draw this. Even using schematic shortcuts, my hand would fall off. I'm just going to simplify all 100 ohm resistors in parallel as a single wide short conductive path with 1 ohm of resistance. Consider what would happen if I put a 101st resistor in parallel to these 100 ohm resistors. This new resistor, however, is not another 100 ohm resistor, but rather a 1 mega ohm resistor, i.e. an extremely large resistance. This extremely large resistance could be symbolized by an extremely long, narrow, and obstacle-laden path. Yes, this single path is high resistance, but what have I done to the total resistance seen by the source? What I've done is I've added yet another path, and I've reduced the total resistance yet again. Granted, only one electron out of 1,000 is going to take the time to grease itself up and get down on all fours and wriggle through that narrow, twisted passage. The point is that one electron now has an additional opportunity to travel through our circuit, where previously the opportunity did not exist. In effect, anything in parallel, even extremely high resistance paths, always reduces the total resistance seen by a source because it allows more opportunities for current to flow. Can we now finally put to rest the fallacy that current takes the path of least resistance? Current takes every path. It's just that more of it takes lower resistance paths because the opposition is less. Regarding actual computation of resistances in parallel, there are a number of formulas available, some more usable than the next. Regrettably, the one most commonly presented in textbooks uses the summation of conductances formula, where conductance is the inverse or opposite of resistance. The unit of conductance was originally known, and I am not making this up, as the mho, symbolized as an upside down ohm. Get it? Mho is ohm pronounced backwards. Not kidding. Look it up on Wikipedia. Actually, do not look it up because I want you to immediately, irrevocably purge your memory about conductances, mhos, and this formula. Do not use this formula. Rip any mention of it out of your textbook, rip it out of your lab partner's textbook, and go to your school's library. Check out all the electronics textbooks, obviously using your lab partner's student ID, and rip any mention of this formula out of those textbooks too. Do not use this formula. For those of you that are still considering using this formula, here's why I don't like it. This formula is like an expensive, indiscriminate, awkward, crew-served heavy weapon. In those rare occasions it's effectively deployed and pointed in the right direction, it's a beauty to behold. But it's of limited practical value in a street fight, and you're gonna get a wrong answer because it's so easy to screw it up. Here's the formula I like using when I encounter an aggressive looking parallel arrangement of two resistors. This formula is small, effective, discriminate, quick and easy to use, and effectively hidden in your pocket, under your shirt, or tucked in the small of your back. It's the slightest provocation. All you got to do is whip it out and start stabbing. Notice my preferred two resistor parallel formula only engages two targets at a time. It's not a machine gun or a cluster bomb meant to annihilate a city overrun with zombies or quell a hippie riot at a Fish concert. That's not its purpose. This formula's purpose is to quickly and effectively take out a target you'll most commonly be presented with, notably two resistors in parallel. Unless your lab instructor is a totally sadistic bastard, when are you ever going to run across more than two resistors in parallel? Now I know some of you just about rolled your eyes out of your head and sighed, Jim, come on. Every lab instructor is a totally sadistic bastard. It's in the job description. Fear not. You can use this formula more than once. Allow me to demonstrate. Let's say our circuit consists of a parallel configuration of a 240 ohm resistor and a 470 ohm resistor. What's the total resistance seen by the source? Stop. Before you use either formula, remember what we talked about earlier before we even mentioned a formula existed. How big should the total resistance be in comparison to either of the two resistances that make it up? It should be less. How much less? It should be always less than the smallest resistor because there are now two paths in parallel. If you get any value higher than 240 ohms, you're doing it wrong. It helps to have some boundaries before you bound off into the woods. Let's put our final answer in the most appropriate engineering prefix and go down to the 10th place. Use whichever formula you wish. Okay? Get ready, get set, go. Bang. Done. Beat you. Don't tell me I didn't, because I know I did. Here's how I did it in slow-mo. I used the 2 resistor formula to calculate total resistance in one seamless lightning quick draw and fire. 240 ohms times 470 ohms divided by the summation of 240 ohms and 470 ohms equals 158.9 ohms. The hardest part about using this formula in one step is remembering that the order of operations requires you to enclose the summation of our 2 resistors below the division operator in parentheses. If you didn't, you'd get a wrong answer and blow the showdown. 158.9 ohms is less than our smallest resistor. I've got a feeling we're right. If you stepped into this fight swinging a bunker-busting fuel air bomb in the form of our sum of conductance formula, you might eventually get a right answer, but it's going to take a long time for you to call in an airstrike. Because some of you are really hard-headed, let's just try this out the slow and old-fashioned way. 1 over RT is equal to the summation of 1 over 240 plus 1 over 470. Remember, we are trying to solve for RT, which means we've got to take the inverse of our final answer. Notice all the asymmetry and parentheses and operators and inverses in there. I am really good at using my Chinese instrument CI89 calculator, but I am fully confident I'd dork this up if I try entering this all at once. Regardless, after a couple of agonizing seconds of trial and error, you're eventually going to come up with 158.9 ohms. After a couple tries. Do not lie to me. I know you dorked it up the first time. I'm watching you through your webcam. I suggest you put on some pants while you watch these lectures. Second parallel resistance example. Let's say a trio of ornery looking resistors stalk into a saloon. The trio is composed of a 240 ohm, a 390 ohm, and a 470 ohm resistor in parallel. Go get your Gatling gun, and I guarantee I'll have this trio of resistors subdued into a single simplified equivalency by the time you even set up the tripod using my preferred 2 resistor parallel formula. How might one use a 2 resistor formula for a 3 resistor parallel relationship? The answer is cunningly. Use the same tool twice. I know it seems like I'm promising twice the work, but am I really? Each single repetition of the 2 resistor parallel formula is substantially lighter work than using our all-encompassing parallel resistance formula once. Additionally, each repetition, because it's lighter work, has a much greater chance of success than a single repetition of a messy and complicated formula. What do you want? A wrong answer after a lot of confusing work, or a correct answer after 2 easy moves? I know what I'd choose. Again, before we begin, we should expect our final simplified equivalent parallel resistance to be less than the smallest resistor in our parallel arrangement. In this arrangement, we've almost got a case of a 240 in parallel with a 470, which we already solved in our previous example, in parallel with another 390 ohm resistor. So our total resistance should probably be even less than our previous answer. By the way, there's a hint hidden in there. Here we go. We already know that a 240 ohm resistor in parallel with a 470 ohm resistor is 158.9 ohms. Just replace those 2 resistors with their parallel equivalent of 158.9 ohms. Now, what's 158.9 ohms in parallel with a 390 ohm resistor using our 2 resistor formula? 158.9 times 390 divided by 158.9 plus 390 yields us 112.9 ohms of total resistance. Bang. Done. 2 easy steps. Now I know some of you are saying, wait a minute, no fair, you cheated. Did I? Did I not warn you I was going to do this cunningly? Some of you might be taken aback by the fact I took our trio of parallel resistors out of order and then engaged a pair at a time. This isn't cheating. Quite like our earlier discussion about the sequence of series resistors, does order really matter when all these parallel resistors are connected to the same 2 nodes? Try this in lab. Look deep into your lab partner's eyes and grasp their hands in yours. Right hand to right hand, left hand to left hand. Warn them you're going to do this though, because I don't want you to get kneed in the genitalia if your lab partner isn't into this sort of stuff. Point your right hands at the ceiling and your left hands at the floor. The ceiling is the positive terminal of a voltage source and the floor the negative. You and your lab partner are now in parallel with one another. Now, have the clumsiest, most awkward person in your lab, trust me, it's more entertaining this way, join you in a parallel relationship. Right hand to right hand, left hand to left hand. All three of you are now in parallel. Now, without letting go of your hands, have the clumsiest and most awkward person in lab try to step over your lab partner's arm and through the space between you. Take turns and do this exchange several times until someone gets hurt. Notice at no time did anyone's hands ever leave the single node at the top of our parallel relationship, nor did anyone's hands ever leave the single node at the bottom of our parallel relationship. Order doesn't matter when you're all hooked between the same 2 points in a parallel relationship. This simple fact can be used to your advantage in parallel arrangements with more than 2 resistors. Engage targets 2 at a time using the 2 resistor parallel formula in whatever sequence you wish. Take advantage of shortcuts, and not only will you get an answer quickly, it'll be correct. Let's try this 3 resistor example the hard way just to check our work. 1 over RT would be equal to 1 over 240 plus 1 over 390 plus 1 over 470, where RT would be equal to 1 over 1 over 240 plus 1 over 390 plus 1 over 470 eventually yields the same answer, but with a more confusing formula and the very real possibility of screwing it up hanging over your head the whole time. Additionally, this all-encompassing formula is an indiscriminate machine. All you get is a single result. Notice that by using our 2 repetitions of the 2 resistor parallel formula, I obtained an intermediate result. This may not seem important to you at this time, but trust me, in later more complicated circuit analysis situations, the availability of intermediate results is a major bonus. You'll appreciate this tip in the future. I want you to get some practice using this 2 resistor formula in situations with more than 2 resistors. Try it again using this same trio combination, but this time combine the 240 in parallel with the 390 first, then combine that with the 470. You should still get the same answer of 112.9 ohms. By the way, the shorthand I'm using here with the double pipes between them, 240 double pipe 390, it's kind of just shorthand for parallel. If you still want more practice using the 2 resistor formula, try the 390 in parallel with the 470 first, and then combine that intermediate answer with the 240 using the 2 resistor formula. Again, your answer should still be 112.9 ohms, proving that the order of engagement does not influence the final result. Before we wrap this lecture up, let's try a couple example problems of resistances in series and parallel relationships. Before you even think of numbers, just look at the problems I'm giving you. Figure out if it's a series or inline relationship, or a parallel or side-by-side relationship. Pause the lecture and see if you can come up with the same results I do. If at any time you're less than confident of your ability to do this by your own, by all means, watch me walk you through the calculations. If at any time you're having trouble with a particular concept, rewind this lecture to that concept and hit it again. Do not advance to the next lecture of the Basic Electronics series until you can do this confidently and correctly. Because I'm super nice, I'm going to throw you a bone. The total resistance of identical resistors in series is always that individual resistance times the number of individual resistors. Makes sense. 3 100 ohm resistors in series is 3 times 100 or 300 ohms. Second trick. The total resistance of identical resistors in parallel is always equal to that individual resistance divided by the number of individual resistors. It makes sense, as 100 divided by 3 equals 33.33333333 ohms. These 2 identical resistor shortcuts just save you time. That way you got more time to hang around in lab and look cool while your lazy lab partner is still struggling. Okay, first up in our example problems is this relationship here. Is it series or parallel? Pretty obviously it's the series relationship because there is one path. In this case, all you got to do for a series relationship to determine the total resistance seen by our voltage source is add them up. Do you need a formula to add numbers? My only advice is pay attention to the engineering prefixes. Don't just walk into a pit trap and say 2 plus 2 plus 1.2 plus 820. Look at it. 2.2 kilo ohms, 1.2 kilo ohms, 820 ohms. We should be getting 4,220 ohms or 4.22 kilo ohms. If we wanted to approximate to the 10th place, we could say it's approximately 4.2 kilo ohms. Next example, what's this? Before you put any numbers in there, is it a series or a parallel arrangement or something we may have never seen? It looks a little different than other parallel arrangements, but realize it really is a pure parallel arrangement. Think about it. I know the schematic shows the 2.7K and the 6.8K in close proximity, but really all three resistors are going to the same two nodes. And we can redraw it like this or like this, whatever floats your boat. Regardless, the source current still has to divide into three separate paths, and this is a pure parallel arrangement. I'm going to use the 2 resistor parallel resistance formula and take out the 2.7K in parallel with the 6.8K first, where that's 2.7K times 6.8K divided by 2.7K plus 6.8K, where that's roughly equivalent to 1.93K. Now this imaginary 1.93K resistor in parallel with a 3.3K resistor using the 2 resistor formula yields 1.93K times 3.3K divided by 1.93K plus 3.3K yields 1,218.829 ohms, bringing it to our most appropriate engineering prefix down to the 10th place, we're approximately at 1.2 kilo ohms. If you gauge any pair in any sequence imaginable or use the complete parallel resistance formula, you're still going to get close to this same value. Next up is this odd arrangement here, consisting of a switch with 4 different positions and 4 identical 1 kilo ohm resistors. Is this a series or a parallel arrangement? It looks weird, but think about it. It's a series relationship. As conventional current leaves the positive terminal of our voltage source, it travels through the switch, and it must successively pass through every single 1 kilo ohm resistor before it reaches our light bulb at the end. Now in this case, where conventional current must travel through 4 1 kilo ohm resistors, the total resistance is 4 times 1 kilo ohm, or 4 kilo ohms of resistance. We're assuming in this case the light bulb's resistance is negligible. Now given this as our starting scenario, what would happen if someone flipped our selector switch to position 2? How would current travel now? In this case, it would have to only pass through 3 1 kilo ohm resistors, and our total resistance is 3 times 1,000, or 3 kilo ohms of resistance. And if we've dropped the resistance, the current should go up and our bulb should get brighter. What happens if we move the selector switch to position 3? In this case, conventional current would only have to travel through 2 1 kilo ohm resistors, or 2 kilo ohms of total resistance. Again, resistance went down. Current should go up and our bulb should get brighter. Finally, let's move our selector switch to position 4. In this case, current only has to travel through 1 kilo ohm resistor, and our total resistance has decreased yet again. And if resistance has decreased, current should go up and our bulb should be brighter still. In every single case, it's a series relationship, and just by changing the position of the switch, we're changing the resistance of our path. Now again, assuming our light bulb has 0 ohms of resistance, an obvious fallacy, what would happen if we put a 5th position on our switch and changed our selector switch to this 5th position? In this case, there is no opposition. In this case, we get a tremendous surge of potentially damaging current until our light bulb filament simply melts, becoming an open, at which point all current flow ceases. The moral of the story is, always have resistance in a path. Consider this arrangement of 3 switches and 3 resistors. If all 3 switches are open, we've clearly got a case where there is an infinite resistance seen by the source, because there's no way conventional current can flow through an open switch. If, however, I close switch 1, what's the resistance seen by the source? In this case, it is only the 1.2 kilo ohm resistor. If I just close switch 2, obviously, the source only sees resistor 2, or 600 ohms of resistance. Finally, if I close switch 3, resistor 3 is the only one in the loop, and the source only sees 300 ohms of resistance. Those 3 iterations should have been pretty easy. The real fun begins when we start opening and closing these switches in different combinations. Say, for example, I kept switch 3 closed and closed switch 1 simultaneously. In this case, it's a 1.2 kilo ohm in parallel with a 300 ohm resistor, or 1.2K in parallel with a 300 is equal to 1.2K times 300 divided by 1.2K plus 300, or 240 ohms of total resistance for the switch 1, switch 3 combination. If I were to close switch 2, in effect what I do is bring a 600 ohm resistor in parallel with our earlier imagined 240 ohm resistor, where 600 in parallel with a 240 is equal to 600 times 240 divided by 600 plus 240, approximately 171.4 ohms. This resistor bank combination is super handy because simply by playing around with these switches, you can come up with a bunch of different combinations of resistances between our two nodes of interest. To add further versatility to a resistor bank such as this, you can add more banks in parallel, thereby increasing the range and granularity of available resistance combinations. This method is featured prominently in the Labo electromechanical systems trainers. Here's a seemingly simple arrangement of a 2 kilo ohm resistor connected to a single voltage source. In this case, it's neither series nor parallel because it's just a single element. But now, consider the addition of an extremely low resistance in parallel to this 2 kilo ohm resistor. For example, a short or an errant wire or an improper connection across the terminals of our 2 kilo ohm resistor, or for that matter, since they're the same nodes, across the terminals of our voltage source. Let's say this low resistance short can be modeled as something with 0.1 ohm resistance. Again, incredibly small resistance in comparison to our 2 kilo ohm resistor. What happens now? The answer is something dangerous. This is the reason why errant shorts are to be avoided at all costs. Think about it. A parallel arrangement of resistors is always less than the smallest resistance. Our smallest resistance is 0.1 ohms. Think about it. If that's a small resistance, we're only going to get smaller still. Run the numbers. A 2K in parallel with a 0.1 is 2,000 times 0.1 divided by 2,000 plus 0.1, or 0.099 ohms. Yes, the 2K is in there, but the 0.1 ohm resistor is making the total resistance seen by the source extremely, extremely low. And if the resistance is low, the opposition to current flow is low. In this case, current could potentially surge to dangerously high levels, in which a majority of it travels through the short, and a small predictable portion of it passes through our 2 kilo ohm load. Again, errant low resistant paths in the form of shorts are to be avoided at all costs because they allow for low resistance or low opposition paths and incredibly high currents. What about this relationship of a 470 ohm resistor, a 680 ohm resistor, and a 390 ohm resistor? What is the total resistance seen by the source? It's a bit of a trick question here because this is neither a series relationship nor a parallel relationship. This is a series parallel relationship, and this is the ambush I warned you about early in the lecture. It needn't be that hard though, because think about it from the perspective of current. As conventional current leaves the positive terminal of our voltage source, it must go through the 470 ohm resistor, and only then does it have a choice between two different paths. What we could really think about this as is the 470 in series with the parallel combination of a 680 and 390. Symbolically, we could represent it like this, and graphically, we could represent it like this, where a 680 in parallel with a 390 is 680 times 390 divided by 680 plus 390, or 247.9 ohms. If a 247.9 ohm resistor is in series with a 470, this can be further simplified as a total resistance of 717.9 ohms. Again, if you ever approach with a series parallel arrangement, imagine as if you're current traveling through a circuit. If you must go through something, it's in series. If you have a choice of going through something, it's in parallel. Let's try another series parallel example. Here's an arrangement of a 220 ohm resistor in series with a 300 ohm resistor, and those resistors are in parallel with a 470 ohm resistor. What's the total resistance seen by the source? In this example, conventional current enters this node, at which point it splits up. A portion of it goes through the 470, and the other portion must go through a 220 and a 330. In this case, the branch on the left is a series combination of a 220 and a 300, but this series combination is in parallel with a 470 ohm resistor, where a 520 in parallel with a 470 is equal to 520 times 470 divided by 520 plus 470 is equal to 247.9 ohms. In effect, what we've done is a two-stage simplification, where the 220 in series with a 300 is a 520, and that 520 in parallel with a 470 is a 247.9 ohm resistor. Again, these series parallel relationships need not be confusing if you simply visualize the circuit from the perspective of traveling current. Consider this configuration of a 390 ohm resistor, a 910 ohm resistor, and a switch. In the case of an open switch, there is a perfect series relationship between our 390 and our 910 ohm resistor because there is no way current can travel through an open switch. In this case, our total resistance is 390 plus 910, or 1.3 kilo ohms. However, if switch 1 closes, we do have a path through our closed switch. Now I know I've said the resistance of an ideal closed switch is 0. Let's get as close to 0 as we possibly can. Let's say the resistance of the closed switch is 0.01 ohms. Again, what we've got is a series parallel combination, where this circuit could be simplified as a 390 in series with an imaginary resistor, which is the parallel combination of a 910 and a 0.01 resistor. Again, realizing parallel combinations of resistors are always smaller than the smallest resistor. Don't even worry about the numbers. That parallel combination of a 910 and a 0.01 is effectively a 0 ohm resistance path. What's happened here? Well, just by closing this switch, we shorted out the 910. When the switch is closed, the only resistance seen by the source is the 390 ohm resistor. In this case, in the open configuration, we went from 1.3 kilo ohms of total resistance, and in the closed configuration, we went down to 390 ohms of resistance. Resistance dramatically decreased, and we would expect the current to increase because the 910 ohm resistor is shorted out and effectively removed from our circuit. This just goes to show you having an additional current controlling device in there like that 390 ohm resistor potentially save your circuit. Alright, let's take a break from our examples and review what we learned. And wow, we really learned a lot. I know the title of this lecture was Resistors, but think of the objectives. We discussed resistors for like 2 seconds. There's really not that much to discuss about resistors for our current desired level of understanding. Seriously, I cannot understand how textbooks of ill repute can spend 40 pages on this topic. Resistors resist or control charge movement inside an electrical circuit. The rest of the time we spent discussing very important properties of circuits, namely a circuit or closed path must exist for current to flow. The physical arrangement of devices within our circuit dictate how that current flows through it. A series circuit is a circuit with one path for current. A parallel circuit is a circuit with a choice of paths. We discussed shorts and opens inside various circuits, and finally I threw you to the wolves and laid a couple series parallel circuits on you, and you did just fine. Yes, you might be bleeding profusely and exhausted, but you'll be okay tomorrow. If not tomorrow, maybe the next day. In all these circumstances, we use visualization and simplification techniques that quickly, directly, and efficiently arrived at a correct result. Despite the fact that this lecture covered a lot of important topics, don't rush to the conclusion that you're an expert on this stuff. We haven't even touched an ohm meter yet, and the ohm meter requires special considerations regarding its placement in a circuit that you just can't learn by watching a stupid lecture on your celly on the way to school. That does not mean I'm not going to try to give you a primer on the subject, but it does mean that you got to get an ohm meter in your hands ASAP and figure out how it works in a safe and supportive lab environment. This lecture just dealt with theoretical calculations for total resistance seen by a source for various arrangements of resistors. This is what you would expect to observe in a perfect world. We should anticipate slight variances between these expected results and the real-world observations and measurements. We'll visit variable resistors, the resistor color code, ohm meters, prototype boards, and more in later lectures. In conclusion, this lecture took a close look at a common electrical component known as a resistor. We discussed fixed resistors and introduced 2 important electrical relationships known as series and parallel. We learned to calculate the total resistance value seen by a voltage source using the series summation and 2 different parallel resistance formulas, one of which I have strong affection for and the other nothing but extreme disgust and loathing. Along the way, we discussed basic circuits, and I discussed the influence of shorts and opens inside circuits. Finally, I ambushed you with an early discussion of series parallel circuits, and you either survived to hear this message or died valiantly in the attempt. Remember to review these concepts and practice these techniques as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.